So first of all, homework is due tonight. If you have questions, we can go over them right now. It's just slightly more difficult than the project in that you have to figure out what matrices to assemble, but after that it's very easy. Oh.
Well then, yeah, I'll ask a question for the Euler's and the Range-Kuda methods. You're using the derivative in each one of those, right? So the function that you're multiplying the time step by is just the function, and it's just a function of t, right? Well, why?
So the question is, let me see if I get it. So the derivative in time is given to you here,
right?
And both in Euler integration or in Runge-Kutta integration, you have to use the derivative in time. So yeah, you would use this function given you.
Right, and you're just using your new y for each of them.
When you start at time equals 0, and yeah, you keep stepping slowly in time until you reach the end time, which is equal to. And you can use the time step that's given here. So you step by 0.1 seconds. And this is simple enough that you can integrate it on paper and check your numerical solution.
Right.
The second problem is where you repeat the homework problem from the project 1, but instead of using the simple, easy, explicit time integration, you use the implicit time integration mentioned here. And you'll see this gives you a huge advantage in terms of the dt you can use. You can use much larger dt, but it's expensive. So there's always a trade-off. Okay, so it's relatively straightforward. I have posted the solution for project 1 here. Yeah, so if you just go there, there's very simple codes for the 3 problems you have. I will grade it soon and I'll publish the grade. Okay, anything else? All right, so again, homework is due tonight. Please make sure to submit it. Okay, so last time we were talking about the pressure Poisson equation, and then we got to this mysterious concept of time splitting or fractional step method. It's a very simple concept, but unless you work through very simple examples, it might seem wrong at first. But this concept is used everywhere. Any PDE you solve, if it's more complicated than dy by dt equals 5y, you would have to use something like a time splitting approach. Okay, so today, let's spend some time taking a look at, how can we justify this splitting approach. So there's several names that people call this by. So there's time splitting, or some places you might see it being called operator splitting. Or you might even see fractional step method. And whether you do chemistry, where you look at reaction diffusion equations, whether you do astronomy, whether you do CFD, this fractional step method you will encounter almost everywhere. Okay, so this is just a method for solving PDEs. Which might have multiple operators. Multiple operators. Okay. So what does this operator mean? In our Navier-Stokes, we have three main components. We have advection, we have diffusion, and we have pressure. So each of these is represented mathematically as a different operator, right? So in Navier-Stokes, we have advection, diffusion, and the pressure Poisson. Okay. So, fine, this fractional step method is a method for solving these equations, but what exactly does it entail? So, the idea is very simple. First, you split the original PDE into several parts, okay? Into several parts. Over a single time step. Meaning, when you want to go from step n to n plus 1, you treat your full PDE as several subparts. Okay. Fine, you split it, and then you solve each individual part. Separately. And finally, you combine all of these individual solutions. Combine the individual solutions to get an estimate. Solution of the original. PDE. Okay. So does the concept make sense? You know, at least in an abstract way. So you have the full long original PDE, you break it up into different parts, solve each part separately, and in the end you combine all of the different solutions to get the full solution. Okay? So we solve each part sequentially. Where the output of each sub-problem is used as the initial condition for the next sub-problem. Okay, and we will work through a very simple example today to see what exactly this means. Okay. How do we set the output of each subproblem to be the input for the next subproblem? So let's actually do an example before we talk about the advantages and the disadvantages. So let's see. Let's do a very simple problem. So for example, we might have a simple ODE where you have du by dt so is a function f1 plus function f2. Okay, and you're told that f1 is very simply a times u, f2 is b times u, and you're given initial condition u at time equals 0 is u naught. Do you know how to solve this? I've written it in a slightly complicated way, but you know, if you get rid of the f1s and f2s, it's a very simple
Integration.
Yeah, you can simply integrate it in time. Fine, let's do that. We can solve this analytically. Okay, let's see. This is du by dt is au plus b, right? Which is just a plus b times u. A and b are constants. What is the solution? And let's go step by step. Jumping around is not good.
A plus T plus.
Make sense? Nothing complicated, right? It's just integrated. Okay, how do I find C? How do I find A?
Your initial condition.
I'm sorry, that was a terrible question. So A is actually given, right? Yeah, F1 is AU, F2 is BU. So yeah, just don't confuse A, B, and C. So A and B are given constants. C is the integration constant. And yeah, you're right, you would use the initial condition. So let's see. Initial condition is u at t equals 0, we are told is equal to u naught, which should be a plus b times 0 plus c. So it's basically e to the c. Okay, so e to the c is u naught. I set here delta t, but you could just write t, right? You don't need the delta. So fine, which means u of any general t is e to the a plus b times t and e to the c, which is basically u naught e to the a plus b t. Make sense? Okay, so we have not done any splitting. This is exact. There's no assumptions yet. All right, let's start taking, this ODE apart and make it into several different individual problems. Okay, so let's see. If we had split the original ODE into two subparts, we would get, let's see. So original ODE was du by dt equal f1u plus f2u. Okay, and when we split it, we can say the first part is du by dt equal f1u with initial condition u naught and output u star. Okay, so we will say u star here is an intermediate solution. U star is an intermediate solution. Okay, at this moment you should be a little uncomfortable because, I've arbitrarily decided to break this up and just taken the first part and neglected the second part. What's next? What should I do next?
You should solve it.
I should solve it, yes, but let's finish completing the split first.
So use F2 to get U star star.
Yeah, so that's my second equation. Is du by dt is f2 of u. And what is the initial condition now?
The same thing, you know.
No, actually, see, that's
So
the,
U star.
yeah, that's exactly the idea. You get the solution for part 1 and use that as the initial condition for part 2. With initial condition u star and output
U star star.
u star star, or let's say un plus 1, right? Un plus 1 is what we're trying to solve for. Okay, let's see if this makes sense, if we get an answer that is close to what we should get. Okay, so let's solve step 1. What do we have? We have du by dt is f1 was a times u, okay? So the solution for this, again, you integrate in time, it will be ln of u equal a t plus c. So u of, but u star is actually e to the at plus c, which is e to the at times e to the c. Okay, what is the final u star value? Is anything confusing? No. Not confusing, right? No. Okay. So what should I write? U star equal what?
U naught e raised to 8.
Yeah, u star equal u naught e to the at, right? Because we said initial condition for this subpart is, a u of time equals 0 is u naught. U naught or un. All right, let's solve step 2. Okay, what should I write?
Del U over del T equals BU.
Exactly. Del U by del T will be U with initial condition U of T equals 0 is now U star. Okay? And result or output equal U to the n plus 1. U to the n plus 1 or UT in general. So let's see, if we solve this the same way as before, we will get ln of U equal B to the T plus ET plus CE. And then we have UN plus 1 equal E to the BT plus C. E to the BT times E to the C. Okay? How do I find E to the C this time?
You use U star
Yeah, so we use this new initial condition.
instead.
Okay. So I see for this case is U at T equals 0 is U star, which is basically E to the 0 times E to the C, which is E to the C. Okay. So we get U to the n plus 1 is U star times E to the BT, which is, what was U star? Let's see. U star we found was this
U naught E to the.
All right, let's plug that in. So we have U naught E to the AT, E to the BT. Okay, this is our solution. Okay. Does this match the exact solution?
Not exactly.
No.
Actually, yeah, because it's A plus B.
Yeah, this was the exact solution, right? And now our split solution has given us, which, because we're dealing with scalar values, so A and B are simple numbers, not matrices, this is exactly equal to e to the A plus B times C. Okay. All right, so do you believe now that the fractional step method is a valid approach? In this case, it's exact because we have used a very simple problem. We have used a linear problem, and we haven't dealt with the matrices yet. For the full PDE, the A's and B's are actually matrices. And they introduce an error, and I will show you how. Okay. So let's make a few notes now. Let's see. All right. Solution of the time splitting approach is exact if F1 and F2 are linear in U. Okay, and this is assuming A and B are scalars, not matrices. I will show you what happens when they are matrices. Okay. This is not the case for Navier-Stokes equations. Why is this not the case for Navier-Stokes equation?
Non-linearity.
Which term is nonlinear in Navier-Stokes?
In the momentum equation, the advection terms, U, partial x, for example.
Yeah, so the advection term is non-linear in Navier-Stokes, but the diffusion term is linear. Okay, but you know, the advection will mess this up, so let's see. The advection term u dot lambda u is not linear. U. Okay, so there will be some error. When we use time splitting. To solve the Navier-Stokes equations. Is everything okay up until now? Everything makes sense? Conceptually, everything is fine? You understand what time splitting means? Perfect. It's a very simple concept, but a very, very important one. Okay, and there are several ways of, several techniques you can use for splitting. You know what we did here was, we just broke it up into two parts and took full time steps for F1 and a full time step for F2. You could have done something more, more sophisticated, and that increases your order of accuracy. So we will take a look at that. Right? So the splitting method we used above is referred to as, does anybody know?
Superposition.
No. It's referred to as Godunov splitting. Godunov splitting or Lie splitting. Lie. Okay, and this approach is first order accurate in time. There's another approach called Strang splitting. Is second order accurate. Okay, Godunov splitting is named after Sergei Godunov, and Strang splitting is named after Gilbert Strang. I think he was still a professor at MIT just a few years ago. He might still be there. I don't know if he's retired. But yeah, he has very nice lectures in linear algebra, and they're all on YouTube if you want to take a look. Okay. So yeah, the simplest thing you can do is split in time and take full time steps. Okay, and that's a very commonly used approach. You can do something more complicated, but usually you have to pay in terms of cost. So you almost never would want to go beyond this second order accurate splitting. High order splitting methods exist. but they are not practical. Due to increased cost, increase in cost, and complexity of implementation. You might be wondering, why did we do splitting this way? So, right, let me wait for a few minutes. Okay, so when we did the splitting, we said you will split it this way, right? Split step number 1 is u by dt is f1. Second step is equal f2. Is this the only way to do this? Is there any logic behind taking f1 here? No. It would be equally valid if I had done f2 in the first step and f1 after that. If you do that, you will get the same result. Again, because it's a nice linear problem. But if you think about Navier-Stokes, you have du by dt on the left side. This is a convection term. This is a diffusion term. Think about what happens if you solve the two things separately. If you do diffusion first and then advection, versus if you do advection first and then diffusion, do you expect to get the same answer?
No.
Why not?
One term is linear, another term is non-linear.
Yeah, exactly. So the advection step is non-linear. That is why, if you do advection first, then diffusion, your answer will be something. And it will be different from if you did diffusion first and then advection. Okay. So these two operators do not commute. Advection and diffusion do not commute. Okay. Commute here is the key word. And we can see how this impacts the error. Okay. So we will see that in a bit. Let's see, should be. So let me show you strand splitting first, and then we can go on to talking about this, how commuting operators can ensure zero error. Okay. So let's repeat the example. With strand splitting. Okay, and the steps in strand splitting are first, you take a half step. Take a half time step with the first subpart, subproblem. Okay. Then you take a full time step with the second subproblem. And finally, you take another half step. Again with the first subproblem. So conceptually, this is very simple. It just becomes a little long on paper. So if I gave you Navier-Stokes with only diffusion and advection operators, what would you do to do strand splitting? Is the question clear? So let's say we have a nice Navier-Stokes equation without all the complicated things. It only has advection and diffusion. And just by looking at what's written here, how would you split this nice ODE, this long ODE into subparts? What would you do? You have only two operators, advection and diffusion.
I start with diffusion.
Okay, you want to start with diffusion. Then?
And then take a half a step and we follow this procedure.
All right. So keep going. You take a half step, and then what happens?
And then solve it.
You solve diffusion with half a step. You have a new intermediate solution.
Intermediate solution, and then using that intermediate solution as a initial condition for the advection.
And you use that intermediate solution as the initial condition, but this time for advection.
For advection. Solve with advection to find the UN+1.
Yeah, you solve this advection, but full time step. Okay, that's what's mentioned here. All right. So first, you started with diffusion. You advance for delta T over 2. This gives you an intermediate solution. U star. This U star now goes into solving the advection equation. And there you take a full time step with this U star as your initial condition. Fine. Then you get a U star star. This U star star, what do you do with this U star star? Somebody else.
Use it as the initial condition for the half step with diffusion.
Yeah, use it in the final half step, this time as the initial condition for the diffusion again. Okay. So that's strand split. Okay. And you started with diffusion. Somebody else might have started with advection, and it's equally valid. You start with advection, go delta T over 2. You have a new solution, U star. You do diffusion with this U star, with a full delta T. This gives you U star star. And then you do another delta T over 2 advancement with advection. Make sense?
Yeah, but the error doesn't change if we start with diffusion or advection because one of them is linear.
The error changes exactly because advection is non-linear. Okay. If both operators were linear, it would not matter. Same as here.
Right.
In our very nice linear example, doesn't matter whether you start with F1 or F2. And I will use this example to just quickly go over strand splitting. Here we started with F1, now we will start with F2 for strand splitting. Okay? So everything makes sense? Yeah, it's very simple. You just, once you get your head around it, it makes sense. Okay. So, as we said, let's repeat the example with strand splitting. Fine. So the original PDE is del U by del T is F1 plus F2. Okay, step 1. What should I write? Well, no, let's do this split first. Okay, let's do the split equations. What is the first split? So at the moment we're just breaking up this ODE into subparts.
So it's del U over del T equals F1 view and del U over del T equals F2 view.
Yeah, let's do F2 this time first, okay? So it's F2U. And this initial condition for this will be let's say UN, okay? UN or U0, same thing. It doesn't matter. And what is the step size? Step size is delta T over 2. Okay, and what is the output? It's U star. Okay. The next split equation will be what?
Del U over del T equals F1.
Yeah, equal F1. Alright. And alright, let's initial condition.
U star.
U star. Step size.
Delta T.
Delta T. Result.
U star star.
U star star. Final step. Step 3.
Del U over del T equals F2.
W over delta equal F2. Okay, we'll repeat the equation from the first step. Initial condition.
U star star.
Exactly. Step size.
Delta T over 2.
Result.
U of n plus 1.
Yeah, result is the final answer we are looking for. Makes sense? Is clear? Okay. Alright, let's do the integrations very quickly. So we have split equation number 1 is this. So let's see. So step 1 is del U by del T is equal to EU, which implies with IC U star, which implies U is basically which we call U star. Sorry, is IC UN, which implies the intermediate solution is UN e to the B what?
D.
BT. B delta T over 2, right?
Oh.
We said our step size will be delta T over 2. So yeah, let's write delta T over 2. It's more general. Delta T is just the difference between going from UN to UN plus 1. Fine, what is step 2? Step 2 is del U by del T is AU with IC U star. So we get U of T equal, which is now U star star, is actually U star times what?
A delta.
Yeah, A delta T. It's good? Yeah?
Yeah.
Alright, so let's plug in U star, which is what? U N E D delta T over 2 E A delta T. Okay. So we're just chugging through the numbers. Alright, step 3. What is step 3?
Another half step with
Alright, good.
BU.
VU with IC is this time it's
U star star.
exactly, and this is a half step, a half step. u of t, which is un plus 1, will be u star star times
To the e delta t over 2.
perfect. And we said u star star is this thing here, un e to the b delta t over 2, e to the a delta t, e to the b delta t over 2. Is this correct? Is this what you expect? Yeah, it's the same as before. It's un this plus that, and that is e to the a plus b delta t. Okay? So, strand splitting works as well. And again, we get the exact answer because we used a very simple example. But if you used a complicated example where it's not exact, this approach would be second order accurate in time. The first approach is first order accurate. And here too, you don't need to start with F2 here. We started with F2. You could have started with F1. So this will be F1, F2, and F1. Okay, so we were working with very straightforward analytical solutions here. Let's do splitting with, let's say, the advection diffusion equation. Okay, let's try splitting with the advection diffusion equation. Do you know what the advection diffusion equation is? You know what the advection equation is. Okay, do you know what the diffusion equation is? You combine it, right? So, let's say we do advection of a scalar. So dy by dt and do you know what goes here?
The advection.
Yeah, which is?
U dot nab.
Yeah, it's the advection term, which is u dot lambda u, lambda phi. We're saying we're advecting a phi, scalar, so this is a linear PDE equal,
Diffusion term.
which is?
Nu del square phi.
Yeah, kappa is diffusivity. Nu we would use when we are talking about velocity, viscosity. Okay. All right, so this is the advection diffusion equation. Let's see, what should we split it with? Should we use strand splitting or Volkoff splitting? Let's do Volkoff splitting. Okay, it's simpler, and you know how to do strand splitting. You could try it on your own. So let's do Volkoff splitting. All right, so we have two operators, an advection and a diffusion. So let's say the split will be, all right, what will the split be?
If we take diffusion first,
Okay.
it should be dou phi by dou t is equal to kappa That's fine.
All right, so you want to take diffusion first, so you would do it like this. Somebody else might say, no, I want to do advection first. Equally valid. All right, now let's see. We have to mention a few things here. What will the initial condition be?
Phi n.
Phi n. What will the step size be?
Delta t.
Delta t. We are doing go-to-node splitting, so we will take full steps. What will the result be? Phi star, yeah? All right, split. The second sub-problem is?
Del phi over del t equals negative u dot nabla phi.
Initial condition?
U phi star.
Phi star, step size, delta t. Result?
Phi n
N
plus
plus
1.
1.
Yeah, that's your final answer. Okay, all right. So this, we just wrote it down. It's still continuous. We need to discretize this bit before we can program it. Okay. So let's see. Step 1. All right. What should we write here?
Phi of I minus 1. No. Sorry. Phi of n plus 1.
Okay, so we said the result will be phi star, right?
Oh yeah, okay, so phi I of star.
Exactly. So phi I star minus
Phi I of n.
phi I n over delta t equal
Phi of I plus 1. N. Minus 2 phi I n plus.
Okay, you know how to solve this. The only unknown here is phi star. Fine. Once you solve this, you will get what phi star is. Solve this to get phi star. Fine. Once you get this phi star, you plug it into step 2. Okay, somebody help me out with writing step 2.
Phi I of n plus 1 minus phi I of star over delta t. And it'll be the same on the other side, but all the ends will be stars, right?
It'll be the same as
Will be kappa phi I plus 1 star.
y.
Oh,
So
I'm
you're
sorry. We're doing u nabla phi.
Yeah. So now we do the advection operator.
Right.
Minus
U of I star or n.
star, strictly speaking star, yes.
Right.
But
This term is n.
in these scenarios, you're affecting phi, a scalar, which might be temperature or ink concentration. And you can assume that this is un. U does not change during the time step. So strictly speaking, U star, yeah, fine, but you can assume this is equal to un. Right, and yeah, we're doing this for 1D, so otherwise you would have multiple components. Over.
2 delta x on the bottom.
All right, 2 delta x, yes.
And then on the top it's phi I of n.
Which operator are you trying to discretize? This one, right?
Right, phi in
Phi
1D,
plus.
so it's only with respect to x, so it's two terms.
Okay.
So it's phi I plus 1 minus phi I
Minus 1.
minus, right?
All of them
For
times n,
stability.
right? Or star is two.
So one thing I'll point out is, in pure advection, we saw that this discretization is not stable,
Right.
but that's for pure advection. When you do splitting like this, this is not unstable, okay? But the time step size restriction can be very small. But in full Navier-Stokes, you can actually use this discretization. It will work. Ideally, you would upwind this, but it's okay for now, right? So does this make sense? This is how we do Gordon splitting. With Schrank splitting, it would be a bit more involved, but you know the procedure, you can do it, right? Any questions?
So I forgot the advantages of second approach to make it into second two
Taking half steps.
half steps.
The advantage of that is it's second order accurate in time. This simple approach is first order accurate in time. So if you need higher order accuracy, you would use the second approach. Again, anytime you improve your computation, you pay. You pay in terms of more memory required and more CPU time required. All right, so let's see. Should I show you the error? It will get confusing. So if you want, to know about this, how if the operators commute, you have zero error. I can show it to you later, or you can Google it. But I don't want to put too much on you right now. Fine. So we discretized this very simple advection diffusion equation. Now, what we really want in CFD is to discretize the Navier-Stokes equation. Okay, we keep doing the same thing. So now we can talk about we can go back to talking about the projection method. Any other questions before that? No. All right. So let's go back to the pressure projection method. For the Navier-Stokes equation. Okay, and this procedure was actually first published by Chorin, C-H-O-I-R-N, in 1969, 69, 67, I forget, around then. Okay, and it's called Chorin's projection method. It's a very classic standard method that most codes use nowadays. Okay, so before we start writing out the equations, what's the advantage of I wish I had mentioned that before. Fine. I will mention that after the equations. Okay. So there are we have a few different options for splitting the Navier-Stokes equation. So the Navier-Stokes equation is again du by dt plus u lambda u well nu lambda squared u minus lambda p over rho. Okay, so we have several options. Of discretizing this equation. Alright, let's see. So, one is do advection, then do diffusion, then do pressure projection. What is an alternative?
Diffusion, advection, pressure.
Yeah, you can do diffusion first, then do advection, and pressure projection. What is another alternative?
That's the only.
That's all.
Yes.
There's one more. You can do advection and diffusion simultaneously. Okay, you can do advection and diffusion simultaneously, and then you do pressure projection. Why would I pick one method or the other? So, okay, here, doesn't matter if we do these, either the left column or the center column, okay? It's just a matter of picking the operators differently. Why would I prefer this over that, or, the other way around?
The third one will have less errors, right?
This will have less error. Why?
Because we are not splitting them.
Yeah, your point is correct. You're saying we do this together, so we did not split these two, okay, as we are doing here. So we reduce the amount of error we introduce at each step. So why don't we follow this method all the time? Why do we consider this? It might be, you might have an advantage in discretizing advection and diffusion differently. For instance, you might want to do explicit time integration for advection. But for very low Reynolds numbers, the diffusion can be a very big problem. The time step becomes very, very small with explicit time stepping. Okay, I will write this down after I discretize the equation. So you could potentially say, I will use explicit time stepping for advection, implicit time stepping for diffusion, and then pressure solve will be the same, either left column or right column. Okay, so I will write that out, but before, let's do the splitting. Okay, so let's see. Help me out. What should I write for the first split?
Dou u by dou t equal to d nabla square u minus u dot nabla.
Initial condition?
Un.
Un. Step size?
Depends on what?
Which
Let's take the simple one. Okay, let's go with Gordon splitting.
Delta t.
Delta t, result?
U star.
Perfect. Split 2.
Del u by del t equals delta p by rho.
Minus delta p over rho. Right? Initial condition.
U star.
Star, step size, delta t, final result.
Un plus 1.
So let's pick one of these now. Let's go with the first one, convection diffusion projection. Split one, someone else. What's split one? So let's do advection first. What should I write?
Dou u by dou t is equal to minus
Alright.
u dot nabla.
Equal minus u dot nabla. Right? So we said, okay, fine. Split one will take only advection into account, so ignore the others. This will give us, so initial condition u n, step size delta t, result u star. Okay, split two.
Dou u by dou t equals d nabla square u.
Nu.
Yeah.
Nabla squared q. Initial condition u star, step size delta t, result u star star. And I would write the final step. Split 3 is the same as on the right hand column. Del u by del t is minus nabla p over rho. Initial condition u star star, step size delta t, final result u n plus 1. It is clear? Everything makes sense? So that's how you solve the Navier-Stokes equation, the momentum equation. Okay? So we know how to discretize this. We know how to discretize this. We looked at it a few lectures ago. The only problematic part is this one. Okay? And you see that it's common to both approaches. And it has to be the very final step. Reason being, it helps us enforce continuity. It will help us ensure that nabla dot u is equal to 0 at the next time step. Okay. Let's write the discretization in 1D. So discretized version in 1D. For the steps will be okay, the same way as we discretized advection diffusion previously, we will do the same here. Okay, so we said we have u star I minus u n I over delta t. So this is step 1. Equal minus ui plus 1 minus ui minus 1 at n over to delta x. Step 2 is find out u star from here and then do this u star star I minus u star I over delta t equal nu times u I plus 1 minus 2i all at star over delta x squared and final step is, yeah, what is the final step? So this is the important one and the problematic one.
U of I plus 1
U of I n plus 1
minus U of I star star over delta t. -1 over rho. P of I plus 1 minus 2 pi.
The first derivative, right?
Oh, yeah.
See, what goes here?
Star.
No, actually. So here we put n plus 1. Okay? And yeah, it's the same whether you do the first column or the third column. Let's see, it's the same exactly. So, you know, you would have u star on the right side instead of star star. Okay? So, all right, we have this, and now we want to enforce continuity. Now we must enforce continuity. That is, we must ensure that nabla dot un plus 1 is 0. Okay, so I had written the discretization in 1D. If we just write the generalized 3D form, it's just un plus 1 minus u star star over delta t equal minus 1 over rho a nabla b of n plus 1. Okay, I've just written this in its original general vector form. Okay, how do we enforce continuity? You know that you want nabla dot u n plus 1 to be 0. What should we do to this equation to use that knowledge?
Both sides we do delta dot.
Yeah, you take the divergence of the whole equation. Okay? So what you get is nabla dot u n plus 1 minus nabla dot u star star over delta t equal, let's assume rho is constant, you get nabla dot nabla p n plus 1. Make sense? Alright, what next?
The LHS should be 0.
The whole left hand side should be 0?
Only that one.
Only this term?
Yeah.
Yeah, so this term is 0 because that's what we want to enforce. Okay. And what's remaining is basically rho over delta t nabla dot u star star equal nabla squared t n plus 1. Okay? Okay, I will just flip it so you see nabla squared t n plus 1 equal rho over delta t nabla dot u star star. So, will this term be 0 on the right hand side? Will this nabla dot u be 0? Why not? It's incompressible flow, it should be 0.
That's a, can we say continuity at the, for u star star?
Yeah, logically it might make sense, right? That nabla dot u star star should be equal to 0. But no, you know, because this is an intermediate solution.
Intermediate.
And we never enforced that this should be 0. That is exactly what we are trying to do now. So this intermediate solution will not be divergence free. Okay. But once you say this, then you can ensure that your un plus 1, the final step solution, is divergence free. How do we do that? Do you know how to solve Poisson's equations? I will show you next class how you actually can solve Poisson's equations. So this is just saying, if it were 1D, this is just saying second derivative of p with respect to x is the right hand side. The right hand side is known. Now the problem is, I know the second derivative, how do I find the p? Okay. So that's the most problematic step in Navier-Stokes solution. And it's the most expensive. Okay. So once we solve this for p n plus 1, what can we do? Once we solve this Poisson's equation, for p n plus 1, what is the next step?
un plus 1
Find u n plus 1. How do I find u n plus 1?
by putting it in the discretized equation.
Yeah, this was my discretized equation. Okay, it's saying if I know u star star, if I know p n plus 1, my u n plus 1 can be computed easily. So that's how you do it. Find the pressure, take the derivative, and plug it into the equation. So we get u n plus 1 is basically u star star plus minus delta t over rho lambda p n plus 1. Everything is known now. U star star is known, p n plus 1 is known, you can compute the derivative. This is your final solution. So that's it. That's how you solve incompressible Navier-Stokes equations. Make sense? Any questions? Okay, so yeah, we will eventually get to programming this and solving fluid flows. I will put up the next project either today or tomorrow, but please make sure to submit your homework. And if you have questions, email me. Right? Anything else? Okay, so I will see you next class.